In this video, I want to show you how to use the Neo4j graph database with Quarkus by using the Neo4j OGM Java model. Neo4j is a graph database, and it's especially interesting for applications where we want to use some enhanced or different queries for querying our data in a different way like we would in a typical relational database. And there is support for Neo4j in Quarkus, but for now the support only includes the standard Neo4j Java driver. So what you can do in a Quarkus application, you can use the Neo4j driver by injecting this driver by using the Quarkus Neo4j dependency. But this is, well, only the normal Java driver and not the OGM driver that is enhanced with this OGM mapping model that you probably will be familiar with if you know things like JPA. That will be this on the relational database side. And what I have here, I prepared a coffee example for you where I will show how to use this in a Quarkus application. So what I have a Quarkus application here, some playground that uses this Quarkus Neo4j dependency and also Neo4j OGM. With the Bolt driver to access my database here, and this is what I will use. I configure my database that I can run actually here in a Docker container. So I have a script that starts up Neo4j database in version 4. Let's quickly do this. So I can say run my graph database here, and then it will start up that database in an empty state. And then I can show you how to use this here. I have some model that I just quickly want to show you. So let's start with the graph model actually. And what I have some test data prepared with some coffee beans and, well, some flavors and bean origin countries. So we'll show you a little bit of that. What we will do here, we will run a Cypher query to basically get the data into the database at first. It's very similar to what you would do with SQL. And now I can use this Neo4j database browser to have a look at the graph that we now have. So in our graph, what we start with is so-called coffee bean. So this is the example of some beans that we would have. So for example, if you go to a coffee shop, in the better shops you can select, well, which type of coffee bean you like to have. They have different origins, they have different flavors and all these things. In Java, so that you get an idea, this looks as follows. We have a coffee bean here where you can already see there are some OGM annotations from Neo. And while the coffee bean, it has a name, I just put all of the properties here public, like we would do using the ORM model in Quarkus for a normal relational database. And we have some, well, origins. So a coffee bean has some origin, has a specific roasting grade. So it's a light roast, a medium, or a dark roast, depending on what you prefer. And it has a certain so-called flavor profiles. We're going to have a look at what that is. So in the graph now, we will see that these are the typical beans. They have some, well, interesting name, and they are from some country. So if we double click on them, we already see that, well, there is something special about them. They have these relationships. Let's examine this on the left at first. What it has here, it has, well, some relationship with this green dot that is a country, that is the origin. So you say, if you can see this here is from the origin, and this relates to this relationship here. The coffee bean is from one or more origins. Okay. And also, while we have this flavor taste, so that's already interesting because that's a special type of relationship where the relationship, the arrow in your graph model has a property. So it says, well, a flavor profile here, it means the coffee bean tastes like a specific flavor and up to a certain percentage. So you can have multiple, well, flavors, and then you say, well, it tastes 50% like chocolate and, you know, the remaining so and so. And the flavors will be, this comes actually from some coffee specialty background. There are some different typical flavors that coffee beans taste like in this so-called flavor wheel. And we say, well, to so and so much percent we have these flavors in our roast, in our coffee beans. And this is expressed with this relationship, tastes, and the relationship has a percentage. So can say, okay, this tastes like, fruity or floral tastes, but we can say, well, more specifically, it tastes like 70% fruity and 30% floral. So this is expressed in these relationships. So now you can model this already in a quite detailed way to say, well, the coffee beans, now again in Java, has this flavor profiles, these flavors, and we can say, well, one of these flavor profiles is the flavor that is fruit for, what did I say, 30% and 70% floral taste, or the other way around. This, by the way, is a Java class that represents the relationship itself. So we can say that's a relationship entity, which in the graph is actually just that arrow, just that relationship with a specific percentage here. So now, by doing that, we can model this in our graph. And then also what we have, what you see here, we can ignore all the other ones for now. A country has a relationship is known for a flavor. So typically when you grow coffee beans, you can say, well, there is a certain probability that coffee from Colombia tastes in a certain way, or typically these flavors are represented by these origins. So this is mapped here. We have our country, our origin, which is also an entity, a node in our graph, has a name, and it is known for certain flavors. So that's more like a stereotype to say, well, typically country from Colombia tastes in this way. And that might be interesting later on. So this is how we model this graph. Here in the graph itself, so these are then other beans that taste well differently. We can expand them here as well, all the relationships by double clicking. So you see, you can explore the graph quite nicely here in this graph to say, okay, now we have a different bean here that tastes sweet and fruity. We have this bean that tastes like caramel, chocolate, and nutty for so and so much percent. And also, well, it is from a certain country. And now in this graph, what we can do, we now can map this and access the graph in our Quarkus application. How to do that? So besides using the normal driver that is shown in this guide here, what we do instead, we use the OGM version with the dependency that I included. And this works as follows. I have let's start from this, well, Jack's REST resource. We can access them via REST. I'll show you that in a second. And we have a business component, my coffee beans, which is a CDI application scoped bean that uses an OGM session factory. And that session factory is injected, not per default, but what we can do, I can show you the injection point. No, not this one. I can show you the injection point in the producer. So I produce actually such a session factory, and now I have to do this manually, just that step, to say, please create a Neo4j configuration by using my properties that I have in my properties file. So these are the properties that the usual Quarkus Neo4j would use as well. So that is my configuration credentials here, and then I expose a session factory. And I dispose this at the end as well. And I can use this in this class and say, okay, every time I will open up a new session here, and if I would store something, I would also open and begin and commit a transaction. I have to do this programmatically because there's no support yet in Quarkus here. And by doing so, I can use the session, and now that is then the query of Quarkus OGM. So this session type is from OGM. Which is quite nice because it gives me some handy extra features. For example, I can say get coffee beans, load all the coffee beans from this type, and also map them automatically into this type with a graph depth of 1. So up until 1 extra relationship here. All right, I can show you how this works. So here's my database. I can also run my Quarkus application. Nice story is this already works with the dev mode as well. So I can run Quarkus in the development mode like I'm used to. I could also run it in the production mode here. And then I can say, well, please curl localhost 8080, go to this specific resource. Let's have a look. That's resource beans. And then I hopefully get all the coffee beans. Let's have a look at this. And then it will now be queried here, and then it will give me all the coffee beans. Let's print that, and this already looks good. I see, okay, great, I have these coffee beans here, like these names from Ethiopia, this other one from Colombia with this specific flavor profile. So you see all the relationships are loaded correctly. So this tastes fruity for 70% and 30% floral taste and so on and so forth. And these are all the beans here. So in this case, I load all of my nodes from the graph that then are mapped automatically to my Java objects using this OGM. And what's also interesting, if I say, well, give me a coffee bean with a specific flavor. So now the query looks a little bit more interesting. If I say, well, match a certain part of the graph, but only where you have specific relationships, right? Where my coffee beans tastes up until a certain degree to a specific flavor, tastes like a specific flavor. And then I can return them. What I have to do here, actually, with the graph, I have to write the Cypher query here in this case myself to say, well, match a certain criteria where I have this relationship tastes of a flavor. You know, I don't query about the percentage. I say just some taste, at least that tastes like the flavor I give here. And then also what I need to match all the relationships here and return them here all with all the possible nodes and relationships. Why? Because then automatically OGM will map this into my class, into my coffee bean. So we will see this a little bit how to test it in a second. But what is more interesting is now a query where especially these graph databases shine. So get coffee beans with unexpected flavors. What this means, I now want to query every coffee bean in my graph where, well, these origins have a known taste, right? Like a typical taste. Where my coffee beans tastes like some taste that I would not expect from that country, right? Where the country is not known for that specific flavor that my coffee bean yet has. So in this case, for example, let's look at the graph, what this means. Colombia beans are known for fruity and floral taste, right? So, and my beans from Colombia also taste like fruit and floral, so no surprises here. But for example, this bean, they taste, well, nutty and, you know, caramel and chocolatey. And Brazil is only known for these two flavors, let's say, but not for that third flavor. So that third flavor is a somewhat surprise if you want. And then I want to return that node, but not this node. And how to query this? Let's have a look at the query here in the detail. What the query does, that's exactly the same query. IntelliJ has a support for a graph database here. What I say, this query, let's have a look at these two lines first. Match all of these structures, these are the relationships, match all of the coffee beans that tastes like a specific flavor and that are from a country where country is known for, where the country is not known for that flavor, right? So where there is at least one flavor where from the same coffee beans, this country is not known for that flavor. So this is, you know, this triangle match. If you think of it like in a graph, coffee bean, flavor, and country, where you say, okay, where the country is actually not known for that flavor, where there is no such relationship for at least one of the flavors. And then this part of the query just says, well, now again, match all of the flavors, known and unknown, just to return all of them. So it basically like rewinds your return statement to return everything that you return the full bean, including all of the properties and relationships. So you see, if you have a closer look at that, you can specify in a very precise way using the Cypher query language what you want to match on. So if you would imagine, well, doing this in a relational database, that's much more complex. You have to write much more code. And here it's very precise by using this descriptive language within the graph to say what you want to select and match on here. And by doing this, we're returning that. So that's the same query here to say, please return all the coffee beans here, match them to this Java OGM type, and then return this list ordered by name. We can test this. So I just now returned all the beans. And if we have a look into our resource, we see, well, we can also match for a specific flavor, and we can also have, I call them special beans, so with unexpected flavors, something special where we say, well, if we go to /special, then only return, well, there will be two matches, this one and this one. Let's have a look using JQ. If we say select this and map the name, then we only have like these two bean names that actually match that criteria, where we have somewhat unexpected flavors. So this is the idea of this special query. Now, how to test it, right? Instead of just having system tests by accessing your endpoint, what you can also do, of course, that is one possibility, to write a test that now tests this JSON for the expected data. What I also do, I write an integration test, coffee beans IT, where actually this is not a Quarkus test, that is a standalone JUnit test. Why? Well, because with Quarkus tests that would also work, but as I showed in my video courses on efficient testing, that will always start up the application, where Quarkus is really fast, starts up in a few seconds, but at the same time I have to wait a few seconds. So this is much faster to say, well, I just want to access it directly. And what I create here is a coffee beans a test double in my test scope that simply sets up the session factory to, well, the same information that I can use in a test database here. So this is already running, and then I can say, well, just please access this. And what test coffee beans does, it just accesses all the coffee beans and, well, see that my test data expects these 4 beans that are in the system, but also checks whether all of the information is correct, and especially whether all of the data are set. So if, for example, your manual query would not return the correct data, then some relationships or some Java references would be missing, and then I can test them for this. So in this query, it's rather easy, because I just use the load all method, and that loads up until a certain depth that I can specify. But if I say get the specific flavors or the unexpected flavors, then in this case, especially in this method, I say test get coffee beans with unexpected flavors. Now I want to just assert that there are exactly 2, and exactly these 2 with all of these information. And now if my query would be incorrect, for example, the country won't be missing all these flavors, well, then the test would fail. Let's try this out. If, for example, I have a mistake here in my query, if I say, well, I just forgot to return the is from and the country relationship and note, if I did not return these and I rerun my test again, now I expect the test to fail, because it tries to assert, or it asserts that this actually is containing my specific data, that this origin is set to my country, but in this case it isn't, so it's missing because I forgot to return it here. And then the test will just verify that this is the case. This is very similar to what you can do in JPA standalone tests if you have a relational database, just to query it to see, okay, if are my queries correct, and are the data, all of them, correct. You could do the same in a system test, of course, but this one just gives you faster feedback while you're developing these queries. So this is the example that returns my coffee beans. I can also show you the coffee beans in a specific flavor. That is like a filter to say, well, give me the coffee beans, but in this case, not all the beans, but just, is this still running? Yes. Just the, let's say, for flavor fruity beans. And in this case, well, it only returns these 2 beans that actually match that flavor. So that's similar. So what I showed you before, where you say, in this query, match all coffee beans that taste like a specific flavor, where that flavor at least exists to a very tiny percentage. And then again, match these to collect all of the data. If that would be missing, it still returns the node, but not with all of the correct related nodes with their relationships, which automatically are mapped by OGM. So this is how to use an example with Neo4J OGM and one example graph. You can have a look at all that code. It's on GitHub, and you can check out the graph yourself, for example, using this handy browser. This is quite nice to just explore the graph, what you have here, and all the relationships. And if you have a look at the Cypher query language, this also creates all of the test data here for the flavors, for the origin countries that I have, and all these beans. And then you can You can put this into a Neo4j database and then try this out yourself by using this Quarkus application that connects to it and returns all the data via REST and JSON. I hope that was helpful. Thanks a lot for watching.